So today we have lecture 18, right? EE341. We will continue the same chapter 12 of Fundamental of Microelectronics by Behzad Razavi. So we will continue the topic of feedback, which we started in the last lecture. So initially, I will give a quick overview of the last lecture. What we did, that we talked about the feedback and we talked about the negative feedback, and we start seeing the impact of a negative feedback on a circuit, in an analog circuit. And the first and the most important was, okay, we need the gain desensitization. Desensitization, that your gain is not affected by environmental variable as freely as it was being done in the open loop. So the feedback ultimately make your gain desensitized to the your environment, meaning PVT variations or any resistance change or any current change or at a high frequency as the gain dips. So that basically it tries to protect your circuit. So that's a benefit. And in general, we know the gain overall gets reduced, but we have a more stricter control. The second thing which we talked about was a gain bandwidth or a bandwidth extension. We normally call that the product of gain and bandwidth remains constant. Okay, so ultimately, if we increase gain, the bandwidth will go down, or if we decrease gain, the bandwidth will go up. So ultimately, the gain bandwidth will remain constant in overall circuit configuration. And we just see some example. Okay, if this is the gain and this is the bandwidth, if I reduce the gain, my bandwidth will increase like this. So this is the second one here. So that's what also we talked about. And the third thing where we concluded the lecture was input output impedance. That also in a closed loop system, the input and output impedance changes by the same factor of loop gain, sorry. And when we talked about this thing, we took an example of a common gate amplifier, and we said, okay, we are not generalizing at this moment, but we concluded something, and I will just redraw the circuit again to emphasize that point. And again, the same thing, we are not still generalizing the same point. So we took, so we took this circuit, that other common gate with a feedback. So here we have some voltage source, which we use for an input, Vin, for example. So here we have RD, and this is an output for us. And then we say, okay, we have enough feedback going from this node. Oh, I guess there's some mistake here. So not like this one. So the feedback is ultimately going to the base of this one. So output was, since a common gate, output should be here. My mistake. So here and like this one. So here we said R1, and here we said R2, and here we said, okay, there is some feedback going to this point, the gate. And when we derive the input and output relation, we said, okay, input Rn. I will directly write the overall expression we derived. You can just look into the last lecture. In general, if we are going to see in an open loop, we said that input impedance will be 1/GM. But in closed loop configuration, the input impedance will be enhanced by the loop feedback time. So that was equal to R2 divided by R1 plus R2, which is K basically, and times A, so GM RD. So initially we have this input impedance, but because of a closed loop, this input impedance goes up basically. And same thing, opposite happens for an R out, where the output impedance reduces by the same amount. That was equivalent to KA. So this is just for your own. K times A. This is KA. Okay, so this is a KA, or a A is for the feed forward path, R2, R1 plus R2 is the for the feedback path. If you just want, I can also write that thing, what we are meaning here. This is a summing point, for example, this is an input. So here, this gain is A, we have an output Y, and we have something K here. Okay, so I'm meaning this Ka here, and this Ka in this configuration, this circuit is R2 divided by R1 plus R2 by multiplied by GMRD. And coming back to the R out, for the R out, we said, okay, if we are living in an open loop configuration, it was RD, ignoring RO as lambda is equal to 0 for easy. But here the R out will be reduced by the same amount, which we just mentioned here, the same amount, 1 plus R2 divided by R1 plus R2 times, let me just minimize it, yeah, times GMRD. Okay, so we also see this behavior, and we concluded, okay, this behavior, we saw that for a common gate amplifier, we are seeing in a closed loop configuration, the input impedance enhances by the time of a loop gain, and the output impedance reduces by the time of a loop gain. And we said, okay, can we generalize it? We said, no, let's wait for a moment. We are going to see this most likely in the next lecture. What we're going to happen? Can we say this generalized term? It's going to happen same thing for the common source or a source follower, but let's wait and see. But at this moment, for the common gate, yes, the input impedance increases by the time of a loop gain, and output impedance reduces by the time of a loop gain. So these three properties in totality we have seen for the negative feedback: gain desensitization, gain bandwidth or a bandwidth extension, and IO impedance. So we saw these three effects. But today what we are going to see different type of amplifiers, and then we are going to link with those amplifiers what they mean. I will try to save this PDF. So let me write one. So, yeah. So then comes the type of amplifier. All of this content is from the same chapter 12. So I will also make sure try to go through the book, because the book is written pretty much nicely and it covers all the aspects. So discussions, sometimes all the discussions we cannot do in the class, but those discussions are pretty much there. So I will start writing in the number, so 12.3. So the type of amplifier, there are different ways. Previously we have seen in the single stage type of amplifier was common source, common gate, source follower, common source degeneration. And that's another type of amplifier which we see in terms of its amplification. Is it amplifying voltage? Is it amplifying current? Is it amplifying voltage into current? Is it amplifying current into voltage? So these four configurations basically are also used, and they are very much helpful. What type of the signal we want to amplify? The first we all know, which we are seeing, is a voltage amplification. Okay, so when we want to amplify the voltage, I'm just going to discuss all of them in a detail, but let me write all of them. The second thing which we normally also, we are seeing all of these things, but now we are giving some names to them. Transconductance. So here I will write, like, we have an input and we have a voltage output. So this is a voltage amplification. Transconductance means we have a current as an input, and what we have as an output, voltage as an output. ठीक है, just make sure transconductance, जिसको हम GM कहते हैं, ultimately input is a current, output is a voltage. So V out by V in, ultimately we are just mentioning here. Sorry, there's a mistake, no, not transconductance. That's what I'm meaning, that is a trans. I out by V in should be transconductance. Here it should be trans impedance, because we are mentioning V out by I in. So input is current, output is voltage. So we are ultimately having some resistance, which we are talking about. So it was my mistake. And then the current amplification. Current amplification means we have an input current and we have output also current. Same thing, now we can have a transconductance. Conductance. Okay, so transconductance means we have a voltage as an input and current as an output. Okay, so ये चार आपके पास overall combinations हो जाते हैं where we use all of these things, and then each amplification have something which we need to mention. For example, if I want to have first one, this is the voltage. Let me write 1, 2, 3, 4. So easy for us to mimic. We don't have to write. So okay, first means voltage amplification. So in a voltage amplification, what we know, if this is an amplifier, okay, having some gain A0. So we are going to have some input voltage here, which is V in ideal world, let's say, and we are going to observe some output V out. If I ask you that, okay, this is a voltage amplifier, what should be the input impedance here? Because that is very much important for us. What should be an output impedance here? It has to amplify a voltage. You need to apply a voltage. You need to apply to a place where there's some voltage and you want to amplify it. So what should be input impedance? Ideally of this amplifier, we all the time we have seen if the input impedance is, for example, less, it's not very much big quantity, the circuit, the some voltage is going to be dropped, right? So this is a source V in. I will drop this area, and this is the input impedance which is seen here, R in. If R in is a smaller value than RS, or R in is not very much bigger than RS, let's say, then what will happen? The voltage will drop here. We want all the V in to appear here. So that's why the ideally in voltage amplification, the input impedance should be infinite. Okay, so that's first thing. The input impedance should be infinite. And what about the output impedance? In voltage amplification, what should be the output impedance? We want all of this voltage to be delivered to an output, and ideally we don't want any loading to happen. So if we don't want any loading to happen, so what we want this R out to be in ideal world. Again, I'm not talking about the realistic. Definitely we don't have infinite, or we don't have zero resistance. There will be some resistance, but in ideal world, the output impedance for a voltage amplifier should be equal to 0. Okay, so that's one thing. And if we want to model it with a simple model, again an ideal model, we mean that we have a V in which is applied to again some open, so input impedance is open. जिस तरह हम लोग common source में input impedance apply करते हैं, and we say input from the gate side is infinite, and we want there should be some amplification happening. That amplification is depending upon gain of the amplifier times V in. And then what we want, it should be short to output. Okay. Now you can observe that how we pitch this thing. We pitch in a way that our V in is equivalent to ultimately applied on an infinite input impedance, and our out is 0. But this is a ideal scenario. Since we don't live in an ideal world, but we have to observe the things in an ideal manner, and then we see the realistic scenario. So what about the realistic scenario here? The realistic will be, there will be some resistance. So I'm just drawing rather at the realistic part. I'm drawing real. Real, what will happen? There will be some resistance here. Okay. So that resistance we can call is R in, for example. So there will be some finite impedance. It's not going to be infinite. It can be very much high in the range of mega ohm, but there is going to be some impedance which you will design. So as a designer, you will put some resistance in your design. You want to go for an infinite, but you might not be able to. Infinite is again some number, but that would be in the range of a mega ohms, or can be in the range of a giga ohm based on your design. Okay, whatever the value. And also the output resistance will not be 0. There will be some R out. That R out can be in the range of ohms to, again, depends upon your design, can be in kilo ohms. Ohms is good, kilo ohms might be not clumsy, but still you can have it. So the real scenario is the one I mentioned on the black, and without the black is the ideal scenario. So then comes to the second notion. For the second notion, we have a transimpedance amplifier. What is meaning by transimpedance? Input is current. So again, we have some amplifier, but this time the amplifier gain is going to be transimpedance, some impedance basically. So I will not write A naught, which is a unitless quantity, rather it's a unit quantity ohm. So that's why I'm writing R naught. And what about input side? I'm applying some current. Okay, there's going to be some current I in being applied here. I in is going here, and I'm just going to come to what will be done output. And output is again a voltage, so that's fine. So I can write directly this thing. V out. If this is the V out, what will be my R out? As the same case of voltage gain amplifier, R out is equal to 0. That's fine in an ideal scenario. What about input? If, for example, we want to mimic again a scenario that we are feeding a current I in to some junction, we have this one junction, and we have some place where we are feeding is this somehow, let's say, and some this thing. If this input impedance is R in 1 and R in 2, if this is 100 ohms and this is 1 mega ohms, where this current will flow? We all know this will flow through the path of 100 ohm. Where there is a less impedance, the current will flow there. And that's why ideally we say the current source has an infinite impedance, so no current will flow back. But in reality, if we mimic in a way we want to send the current, the input impedance will not be infinity, there will be some impedance. That's why the input impedance of the load side where we want to feed it, it should be equal to 0 if we want that current to flow. Again, in ideal world, we want the input impedance on the current side should be 0. So for the transimpedance amplifier, the input impedance should be very much low or almost equal to 0, and an output impedance should be 0 also. So that's somehow another thing. So we can rub this thing easily now. This is, we talked about the ideal scenario. What about the real scenario? So real scenario, something again, we have a 0 input impedance, so we can just have a ground. So we're sending some current I in. Now I in is flowing through here, and output what we want some voltage source. Okay, right, this voltage source is depending upon this I in multiplied by the current, the resistance. And then what will be the resistance? The resistance is going to be here at this moment, V out. Here I'm doing opposite this mistake. So ideal scenario, I am writing as black, ideal, and red I am writing real scenario. So a real scenario, what's going to be? We want some impedance. So both sides, we will have some input impedance in the circuit. This time not in parallel, we will have the input impedance or the impedance in series both sides. So here, let me plug the red one here, and we can drop anywhere, so it should be here. So here R in and here R out. And both of these places, whenever we are plugging this R in and R out, it should be very small. Okay, so you can also link it to the common gate amplifier, which the input impedance is very much small, 1/GM. So 1/GM is somehow, that's why we are feeding current there, and we can use it as a transimpedance. We are going to talk in a moment. So is these things clear? Make sure that we discuss about the voltage gain amplification and the trans impedance amplification. Let's talk about the current and the transconductance. So yeah, so we have a third again here, also 3, the transconductance one. The transconductance, what is the thing in the what is the thing in current amplification? Current amplification, we again it's a current, so we can have a we can write I would let's say write just for the current amplification. What will be the input side? We have an input side, a current source. we have I in going inside, and we have a current. So that's why we will have a I out. We've already discussed about the input side of this input. This should be equal to 0. What about the output side now? Output side, output impedance should be what? Now the opposite scenario, we want all the current ultimately to flow from this point, okay? We want the current to flow from that point, and no current should be going at this point. So what I am saying ultimately, this is, let's say, a current amplifier for you, CA. And if the output impedance of this is load, okay? If load is, for example, 100K, I'm just putting some numbers, 100K, and R out is here, and R out is somehow like this. This is R out, and this value is equal to 1K or even 100K. Half the current will flow from here. We don't want this thing. In this configuration, we want all the current to flow through RL, which is the load where we want to deliver the current. So that's why the output impedance of a current amplifier should be infinite. Okay? So that's the same analogy. Now we can model it and we can draw the realistic model too. So for the model we are having a input current, which we just mentioned. So we have here I in flowing through. We have something flowing at an output, which is again times A1 times I in, okay, and we have this one current moving through I out. Okay, so here we have this configuration which we just designed. We have an input current and we have an output ultimately current. And this is again, as we mentioned, ideal scenario. In reality, we are going to have some resistance. So if we talk about input side, we will have something in the source here. So this is going to be Rin, which is again a very much small value. And here we are going to have something in parallel, R out, but this is going to be very big value, very big value. So make sure this thing, we don't want it to be loaded. We want it to be in the range of a mega or a giga ohm so that it will not affect the working of the circuit. And let's talk about the last one, which is a transconductance. So transconductance, we all of us are familiar where our input is voltage and output is a current. So these configuration we are having, we are seeing almost all of them, but we just didn't might be pay attention or explicitly give the naming, so which we are going to give today. And here, what should I write? GM, because again, it's a not a unitless quantity. We are talking about I out by V in. Okay. And yeah, input impedance kya hogi? We all know the input impedance should be infinite. And the output impedance should be, what should be the output impedance? Just we have seen the current amplification. Again, it should be infinite. Okay. So when we have input impedance infinite, output impedance infinite, we are talking about a transconductance. Transconductance ko model किस तरह करेंगे? We have again a voltage source V in. Let me use the same. For ideal one, I'm using V in. So we have something V in, input impedance infinite. We have a current which is basically flowing through. The current क्या हो जाएगा? Times GM times V in. ठीक है, and then we have something similar जो हम लोगों ने वहां ड्रॉ किया था, I out. ठीक है, ये आइडियल हो गया. रियल के केस में क्या होगा? रियल both will have a very much big real में. Real में we will have a parallel impedance here, R out, and a parallel here, R in. And both of them should be very big. जब भी parallel impedance, we are assuming an ideal impedance in parallel, that should be very much big. Whenever we are talking about series, this should be very small resistance. Okay? So that's what the whole idea is that. So these are basically the 4 types of the amplifier which we normally use And what I'm going to do, I will just draw example of everyone, and you try to identify yourself first, but I will just draw one by one and we can just go through like, is it what type of amplifier and why we need it. Okay, so let me draw one. Like in a real circuit, at this moment we are putting a black box. Now we are using the common source, common gate, or source follower amplifier, which we have seen in our previous one. I'm just using the black one. I feel I'm more comfortable with the black color. So here we have an amplifier, M1. Input is applied on this side, V in. So try to yourself idealize what is the input impedance, what is the output impedance, and where it is they are matching with this overall configuration. It's a nice and it's same practice which you have done, but it will really help you sharpen your previous concepts, okay, and help you to develop or extend on top of it. Okay. This is here just a current source. This means input and output impedance. You can understand what's that. And this is a V out. So so let's first identify. I will use now a different color. So this M1, we are applying an input here. We're taking output here. So we know this is a common source, and we are applying an input on the gate, and we're taking an output at a source. So we know this is a source follower or common drain. Okay. So ये तो हमें पता चल गया. M1 is a common source. M2 is a common drain, let's say, and lambda is equal to 0. So the R0 we can ignore R0, it's infinite. So what type of amplifier it is first among these 4 types which you just mentioned? Let's first see the simple way. V in is में क्या है? Applying on the gate, we know the V in is going to be R in is going to be infinite. So R in is infinite. This means it can be either transconductance or can be a voltage amplification. क्योंकि इसकी input impedance infinite. What about the output impedance? It's something infinite here, but in parallel with 1 over GM2. So what this means, 1 over GM2 is a smaller value. This time मैंने कहा था realistic. So not among these two. If we just go back, we have this scenario. Here, R out in ohms, in kilo ohms. So this means this is a smaller, R out is small. So what is this configuration? The first one, the voltage amplification. So I will use a different color. So this is a voltage amplifier. Okay. And what is the gain of this amplifier? Assuming this is a lambda is equal to 0 or not infinite, this is infinite. So we can write V out by V in. V out by V in is equal to minus GM1 RD. This is a source follower. So since infinite, R0 is infinite, so we assume कि जो आपके पास ultimately this M2 has or source follower has a unity gain. So it's minus GM1 times RD. So that is a voltage amplification. What about another one? Let's draw. Let me draw, taking this space and draw, and then we can move it. So let's draw another one. So here we have, you can see which amplifier we have now. We are applying to the source of an input. The source has an input. Input is a current. So we already know we are putting a bias that it operates in saturation. We are having some load RD. This is a VDD. And then we have going to again our source follower configuration, which you just see in the previous one. And here we are having an output similar to the first configuration. And this is connected again to the VDD. This is M1, this is M2. Okay. And so first thing we can also, the multiple ways, output is voltage, input is current. If whenever output is voltage, input is current, it's a trans impedance. ठीक है, ये तो पहली चीज होगी, trans impedance amplifier हो जाएगा. Input की impedance क्या है? Also if it's a trans input impedance, the input impedance should be ideally 0, but it should be some very much small value, and what we can say it's equal to 1 over GM. So it's a very much small value. That's also fine. And output impedance, agar trans impedance hai, R out also should be very much small. So it's also 1 over GM. We can all see. Okay. Now the thing is that what will be the gain of this amplifier? Gain kya hoga? V out by I in. Okay. Trans impedance. So it's going to be not V out by V in. It's going to be V out by I in. What will be this gain? So ultimately what's happening, we are feeding this current I in, and the same I in will flow from here, and that will multiply by RD, and that will convert it into voltage. So V out by V in will be ultimately RD, since our lambda is equal to 0. So the trans impedance amplifier will be the value of this resistance RD. Okay? So ये आपके पास trans impedance gain हो जाएगा. ठीक है? Make sure to clarify this point. Then comes, let's see an example of other two. So if we want to talk about this configuration, some might somehow become thick. No, it's fine. So if we talk about this configuration, M1 and V in, and we have some current which is flowing I out. So now you can also see that we have input voltage, output current. So it's a transconductance. So we have I out by V in equal to what? Something GM. And what is that GM? GM1. Right, the same which we all the time common source configuration we have applied. So here what will be the input impedance will be ideally infinite, and what will be output impedance? Ideally, at this moment we are also assuming R naught is infinite. Okay, so that's a trans conductance for us. And what about the last one if we want to draw? So we can have again, whenever the input is being applied as a current, we will use a common gate. So yeah, apne yaad rakhna. So it's a current amplification. Let's talk about. So we have an input here, input current hum log feed karenge. You can have other way of using a common source also by putting in a resistance, but ultimately we have resistance ko voltage convert kar rahe hain. So input is I in, output is current. So it's we have 1 over GM as R in. So it's a very much small resistance, and here infinite. Okay. And what about gain? I out by I in. Same I in is flowing through the source, the same will be the drain. So the gain should be equal to 1. That's very much interesting. We talk about a current gain amplification, and the gain is 1. So what is the benefit? It's something similar to buffer amplifier, where we do a voltage input and a voltage output, and the gain is normally equal to also 1, but in terms of voltage. Here we are talking about a current amplification, but the current amplification of 1. So what is the benefit of a current amplification in such configurations? So let me write first this is a current amplifier, and then I will mention what is the benefit with the help of an example. Okay, because you can see, okay, this is the same thing. You are feeding a current through a wire, having a resistance I, and you are saying, okay, I out, and I out is equal to I in. Yes, but there is something more. That at this moment, the input impedance is very much small and output impedance is a very much high. There we are getting mainly the benefit of this configuration. For example, if we have this configuration, okay, I in, and we are feeding to a system which has parasitic capacitance or some capacitance being formed, okay, which is a common thing. And we have some load resistance R, RD, and we have output V out. If we have this configuration, what's going to happen if CP is whatever the value of CP, some values, and RD is a bigger value. We want RD is a very much big, very big value. So what's going to happen because of very big value, what's going to happen? Our cutoff frequency is going to be very much low, and ultimately it will start impacting at a lower frequency. So the bandwidth will be very much small in this circuit. And we don't want this circuit, this configuration. But the alternate we can do, if we can insert a current amplifier at this node, okay, and because now this current amplifier, the pole will be formed between this CP and this 1/GM. So this bandwidth, which was initially low, it will go very much higher. Okay. So the bandwidth height will go at this point. How? Let's draw the circuit and understand this thing. So we have CP at the same point, but now we are feeding a current amplifier. Okay. So this is a common gate amplifier, VB. Same thing now, RD is here. Here V out aa gaya, and this is an RD. So if we do this thing, ultimately what's going to happen, my pole will go far because now the pole is formed by, जो हम लोगों ने last lectures में भी देखी थी, 1/CP times 1/GM. Previously pole किससे form हो रहा था? Previous time pole was formed by 1/CP RD. So because of insertion of this current amplifier, ultimately we shifted the pole far and it's not affecting or coming into our signal band. So that's the benefit of a current amplifier. Okay, that's one of the important factor. So I will stop the lecture here and I will upload another material because that's one material, and another material is related to the current and voltage feedback in a small moment. So I just want to save this recording too.